Hey, what's happening, everybody? So we're going to be looking at the next section in our unit. Should be 3.7, pseudo-random numbers. We've discussed random number generation already, but this right here is going to be looking at randomness in a little bit more detail. So when we observe the physical world around us, we can pretty much generate random numbers from it. And we can do this by measuring random fluctuations, and these fluctuations are known as noise. So when we measure this noise, all right, the proper terminology is called sampling. So whether if we are just randomly sampling static or we are actually sampling musical notes or anything, all right, regardless of what we're sampling, we can generate numbers from all that. So for example, if we measured the electric current of TV static over time, we will generate a truly random sequence. So we can visualize this random sequence by drawing a path that changes direction. And according to each number, the path will change. And this changing of path is known as the random walk. So at each point in the sequence, the next move is always unpredictable. And that's why it is considered true randomness, because it is literally all over the place. And you can never predict where the next direction will be. Random processes are said to be undeterministic, or non-deterministic, I should say. Since they are impossible to determine in advance, machines, on the other hand, are deterministic. All right, their mechanical operation is predictable. It can be repeatable. All right, and you can then form a pattern from its behavior. And in 1946, John Newman was involved in running computations for the military. All right, and he basically came to this realization. Specifically, he was involved in the design of the hydrogen bomb. And in order to do this, among other things, he relied on using a supercomputer of the time, and then the name of this computer was called ENIAC, E-N-I-A-C. So what he used ENIAC for was to repeatedly calculate approximations of processes involved in nuclear fission. But, however, this required quick access to randomly generated numbers that could be repeated if needed. But the problem is that ENIAC had a very limited internal memory. Everything was based off of vacuum tubes with computers back in the day. So storing long random sequences wasn't really possible. So what Newman did, he developed an algorithm to mechanically simulate the scrambling aspect of randomness. All right, and the scrambling of that sequence is basically, it's this. So first, he selected a truly random number called the seed. And this number could come from a measurement of any noise or the current time in milliseconds. Next, what he did was he took the seed and he took the seed, and the seed was basically the input, and the seed was then inputted to a simple calculation. He multiplied the seed by itself, and then he output the middle of this result. Then what you do is you take this output and you use that as your next seed. So if you take, say for example, you take 100 times 100, okay, that would give you 10,000. And then what you do, you have 5 numbers there, you take the 3 middle digits, and then you use those 3 middle digits as your next seed. Now obviously that would be not a good idea, because then you would have 3 zeros, but just trying to show you what he was doing. He was taking numbers, multiplying them, and taking the middle digit, the middle 2 digits, the middle 3 digits, however many middle digits there were, and he was using that as the next seed. And then that would then be the next random calculation starting point. What he would do is he would basically repeat this whole process as many times as he needed. All right, and so this technical terminology for this is called the middle squares method. And it's just basically the first in a long line of pseudo-random number generators that have been created in time. So the randomness of the sequence is dependent on the randomness of the initial seed only. Okay, so same seed, same sequence. I mean, that's basically how it works. So what are the differences between a randomly generated versus a pseudo-randomly generated sequence? Okay, so let's think about this and represent it, each sequence, as a random walk. Okay, random walks seem similar until we speed things up and we look at them over a long period of time. The pseudo-random sequence must eventually repeat itself, and what you would notice is that the random walk would then eventually overlap itself after a certain point of time. All right, so the cycle basically will repeat itself. So the ultimate length before a pseudo-random sequence repeats is called the period. So the period is strictly limited by the length of the initial seed. So for example, if we use a 2-digit seed, then an algorithm can produce at most 100 numbers before reusing the seed again and repeating the cycle all over. A 3-digit number can then expand past 1,000 numbers before having to repeat its cycle over again. And a 4-digit seed can expand past 10,000 numbers before repeating. Though if we use a seed large enough, the sequence can expand into trillions and trillions of digits before repeating through the key difference, and that's obviously the important piece. When you generate numbers pseudo-randomly, there are many sequences which cannot occur. So for example, if we use Alice as an example, she generates a truly random sequence of 20 shifts. So it's equivalent to a uniform selection from the stack of a possible sequence of shifts. So the stack contains 26 to the power of 20 pages, okay, which is a monster size when you actually stop and think about it. If we stood at the bottom and shined a light upwards from this stack of paper, that is 10 to the 26, 26 to the power of 20 high, right, a person at the top of the stack would basically not see the light for about 200 million years. That's exactly how far that the thickness or the height of the stack would be. So compare this to Alice generating a 20-digit pseudo-random sequence. Using a 4-digit random seed, now this is equivalent to a uniform selection from 10,000 possible initial seeds, and this means that she can only generate 10,000 different sequences, which is a vanishingly small fraction of all the possible sequences from the previous stack. So when we move from random to pseudo-random shifts, we shrink the key space into a much, much smaller seed space. So for a pseudo-random sequence to be distinguishable, or for it to be indistinguishable from a randomly generated sequence, it must be impractical for a computer to try all seeds and look for a match. This leads to an important distinction in computer science. So between what is possible versus what is possible in a reasonable amount of time. We use the same logic when we buy a bike lock. Okay, we know that anybody can simply try all the possible combinations. You've got 4 numbers in the bike lock. Somebody can sit there and start with 0000, 0001 and continue on, all right, and try all the possible combinations. And then they eventually could possibly find a match, and the lock will open, they could take our bike. But in order to do this, I mean, there's over 9,999 combinations to try in a 4-digit lock. So it would take them days in order to actually figure that piece out. So for 8 hours, we can pretty much assume that it's practically safe to lock our bike up with that bike lock, and no one will actually steal it from us. So with pseudo-random generators, the security increases as the length of the seed increases. So if the most powerful computer would take hundreds of years to run through all seeds, then we could safely assume it's practically secure instead of perfectly secure. And in pseudo-random number generation, that's pretty much the important distinction, which is true randomness versus acceptable randomness. So as computers get faster, the seed size must increase accordingly in order to combat the fact that computers can solve these problems faster. Pseudo-randomness basically frees Alice and Bob from having to share their entire random shift sequence in advance. Instead, they share a relatively short random seed and expand it into the same random-looking sequence when it is needed. All right, so basically, as we go through here, all right, and we start looking at true randomness specifically, we want to look at how computers do randomness. So basically, true randomness includes processes like flipping a coin, rolling a pair of dice, drawing a card from a shuffled deck. Other examples in nature can include radioactive decay or even the weather. Okay, but true randomness is actually hard to do on a computer. So computers use what is known as pseudo-randomness. All right, so in fact, computers simulate randomness using algorithms, and algorithms generate a sequence of numbers that looks like RAM. So for example, the short sequence that we see over here, all right, we can kind of see a string of random numbers that have been generated. And so ultimately, so here's an example basically of how a PRNG typically would give the PRNG seed that would start a sequence of numbers, which is up here. And then this would be obviously the next rendition. This would then generate randomness and then spit out the output of our random numbers. So, so the formula basically that would be utilized to calculate this would go from the current number to produce the next number each time. So you say, give me, each time you say, give me the next number, it will produce another number in the sequence, and so on and so forth. And these kinds of PRNG numbers are useful in cryptography, computer programming, computer games, simulations, models, forecasting weather, etc. Even in casino machines like slot machines. So in App Inventor, all right, we use the random number generator block, and that basically was our first experience into randomness and random number generation. So if we use the random number generator and we ask for a range between 1 to 100, it will give us a number like, for example, 50, all right, because that is obviously somewhere between the range of that 1 to 100. Okay, but ultimately, how does the PRNG work? Okay, so we need a formula that calculates the next number in a sequence given the current number, because all of the random number generation works off of randomness, and we actually have to have a formula in order to dictate what that next number should be. So, for example, if we had a PRNG that, with the number of 10 as a current number, it might produce a number of 21. All right, so using the formula that you see there, x2 is equal to x1 times 2 plus 1, x1 would equal to 10. Take 10 times 2, giving us 20, plus 1 gives us 21. So the value x2 would be equal to the output after the number 10 gets fed through our random number generator. That 21 would then be the next value that we would use as the input. So we would plug in the 21 here at x1. 21 times 2 would give us 42, plus 1 would give us 43. 43 would be the new random output, and x2 would equal 43. And then it would then become x1 for the next rendition, and so on and so forth. All right. So this kind of formula we see lets us generalize the PRNG formula that will make the notion of our application more abstract. All right, and it will let x basically stand for the current number, or we let x1 stand for the current number. All right, and then x2 will then equal ultimately the output. All right, so again, I'll just kind of go through the next couple slides because it basically goes through. And then it comes back around again. All right, keeps feeding. And then as I explained earlier, the output becomes now the new input, right? And then the new input then gets fed into the equation to find the new output value. Right, and all I'm going through here is, as you can see, it's the same randomness. We're using the new number as becoming, or I should say the output number becomes now the input number, and we see how the randomness just keeps going and keeps going. So but the issue now is as you can see, when we look at this formula, the numbers just keep sequentially getting larger and larger and larger. All right, so even though we might not be, I mean, you probably can, if you look at the number, the displacement between the number values, you might actually easily be able to figure out what formula is being used to generate this random number. And that's actually not a good thing. So what we want to do is we want to make sure that we truly have randomness, meaning that the numbers can scale from high to low, somewhere in the middle, and then back again. All right, so how can we actually get around doing this? And this is where clock arithmetic comes into play. All right, so the concept we're going to talk about now is called clock arithmetic. All right, when you're actually kind of familiar with this already, it's as simple as when you look at a clock. All right, so we figure we're not looking at a military time 24-hour clock. It's a standard 12-hour clock. So if we look at a 12-hour clock, and then 9 o'clock plus 4 hours, in other words, 4 hours after 9 will basically be 9 plus 4, and that value would equal 13. Okay, but we don't look at it as 13 o'clock. all right, what we do is we take the value of 13 and we subtract 12 from it, and then we get the value of 1 as a leftover. So 11 o'clock plus 5 hours gives us 4 o'clock, all right, not 16. So when we add 11 and 5 to get 16, but we take away 12, that will basically give us the value that we're looking for about 11 o'clock plus 20 hours. Well, 11 plus 20 is 31, but if we take away 12 from that, we get 19. And there's no 19 on the clock. So what we do is we can take away 12 again, and now we get 7. So 11 plus 20 hours gives us 7 o'clock. And so at 7 o'clock, arithmetically speaking, is also known to mathematicians as modular arithmetic. Right? So if you ever heard of modulus, modulo, modular arithmetic, that's basically what they're referring to. All right, so it's a factor of 12. We're consistently subtracting 12 away from the operation, and that's because we want to make sure that we're always in the range of between 0 and 12. I'm sorry, 1 and 12, I should say. So we are performing a modulo operation or model population. I'm sorry, modulo operation or modulus. And we can do it by, as we see basically on the screen here, and we can repeatedly subtract 12, which is our modulus in this case, until we get a number between 1 and 12. You can do 0 and 11 if you want, but then 0 would obviously represent the factor 12. But it's probably easier, in my opinion, just to go between 1 and 12. All right? Basically, it's the same thing, though. So some of you may be familiar with this. Basically, it's pretty simple as long as you keep the the standard factor in mind between 1 and 12. All right. So, but if you aren't familiar with it, let's use this notation. So basically, let's do 31 over 12 in modular arithmetic. All right. So basically, what we're doing is long division here, and so we basically divide 12 into 31. All right, and it goes in there twice, all right, and it gives us basically 24. And then we subtract 24 from 31, and that gives us 7, all right, and that is our remainder. So 31 mod 12 is basically, that's basically what we're looking for. We're looking for that remainder piece. Should probably do a better job flipping through these. All right, so 7 is a remainder, and that's obviously, the important factor that we are looking for. So when we think of our random number generation, I mean, ultimately, that's what we are ultimately trying to find, because that is then going to be utilized in our equations to factor in the randomness, and that will allow the randomness to then be larger, and then we'll kind of circle back and be smaller, and in hopes to never ever have that specific pattern of where numbers are just increasingly getting larger or smaller, or it's harder, I should say, in order to figure out the pattern. Right. So, but instead of using the modulus or modular arithmetic using mod 12, what we're going to do instead is we're going to use mod 13. All right, so here that you see here, we have our formula. We have xi plus 1. So it's going to be calculated by taking the initial x and multiplying it times adding. We're going to take the initial xi, multiplying by 2, adding 1 to that product, all right? And then we're going to take the modulus operator, mod 13, of the product of what's in the parentheses there. All right, so we start with the same process. Our xi value is 10, so we plug in 10, all right? And then we have 10 times 2, which gives us 20, plus 1, which gives us 21. All right, and then we take the mod 13 of that, and then that will then give us the answer for our xi plus 1, which is ultimately what we're trying to find. And preferably what we're trying to do is we're trying to find consistent numbers that are between the value of 0 and 11, basically. All right, but unfortunately what happens is that when we actually go through this process, what we tend to find is that over a certain amount of time, we do have repetitious patterns that will repeat itself. So again, 10 times 2 is 20, plus 1, 21, mod 13, 21 divided by 13 would give us 1 with a remainder of 8, all right? And that's the value that I'm looking for. Okay, we're always looking for the remainder, not so much how many times the modulus divides into the product in here. So then 8 becomes our new input starting point. 8 times 2 is 16, plus 1 is 17. 17 mod 3 should give us an output of 4. All right, so 4 becomes our new output. And so when we keep going through and we start monitoring the outputs, 10, 8, 4, 9, 6, 0, 1, 3, 7, 2, 5, 11. All right, so for the first, maybe 10, 12 digits, it's actually really good. All right, the numbers are purely random and we don't know exactly what's happening. But then something happens once we get to that point. We get to the next number, we have 10, okay? We have 10 here. We then have followed by 8 and 4, and we have 8 and 4 here. So unfortunately what happens now is we get into this loop where we have the same patterns repetitiously forming once again. And that's not a good thing, because when it comes into random number generation, you truly want to have as close to pure randomness, even though you're never going to achieve that in computer programs, but you want to get as close to pure randomness as possible, because of the fact that you always want to make sure that you are generating unpredictability. If you could, once predictability is established, then your random number generation just sort of goes out the window from there. All right, so what they do is using the linear congruential random number generation. All right, it's an area of mathematics that really focuses on the generation of pure randomness. All right, and what they do is they use the same equation above, but instead we substitute variables in for the numbers. And the difference being is that what they do is they take these values, rather than having 2 plus 1 mod 13, what they're going to do is they're going to use really, really monstrously large exponents here. And by using large exponents and large values, what you have now is the ability to, instead of having randomness appear after every 12 or 13 linear strings of numbers, you're going to end up having, sometimes maybe millions, sometimes trillions of numbers go by before a pattern is established. So the larger the value that we choose, the larger, or the closer, I should say, of pure randomness that we become. All right, but the problem is that when you use larger numbers, then you're dealing with greater calculations, and you need stronger computer systems in order to generate those random numbers. So it could potentially slow your computer system down if you are calculating extremely large exponential factors, and it's just unfortunately how it is. So it's really trying to find that nice sweet spot in between where you're not hindering computational processing and speed, but you're also creating a large enough spread using numbers in the random number generation formula so that you can produce random numbers so that you don't have any repetitious patterns form to at least, for what we can possibly comprehend. So the good thing is that the way how computers are developing strong enough, and they're getting faster, and they're being able to multitask a lot more, where they can actually handle such large exponential calculations, therefore allowing the random number generations, the number values in the LCG calculations to become that exponentially large. And in doing so, it gets us closer and closer to that pure randomness factor. So I'm probably I'll stop there for today. Then let's just wrap it up. Random number generation is a very important feature used in any sort of modeling or simulations. Because when any scientist, and I know a lot of you, or a good portion of you in class, are looking at some sort of science field, and as a scientist myself, there's a lot of times where data collection is needed. And the data collection is great to a point because it'll show you up to a certain point of how things are or what is going on now. And you might be able to use that data to go back a few years, few decades, whatever the case may be, and then potentially extrapolate, other data bits going even further back in time. But what makes it very, very difficult is what is going to happen in the future. So using models and using random number generation, programs can be written so that the computer can then take the current data, the current trends, and then forecast a random model based off of previous data. And then that forecast, that model that is generated could then be used as potential outcomes of what might happen in experiments, in the environment, even in like the stock market. I mean, you name it. So random number generation is obviously a big thing because of the amount or how much it's used within computer simulations and models. And it is just also, it gets us to that next level of abstraction. All right, and that's obviously in computers a very important thing. In code we talk about refactoring, making your code less bulky and making it more abstract because we want to make it, less detailed. So computer random number generation allows us to reach that new level of abstraction and not be so kind of in the detail of things. All right, so that being said, why don't we end there for today? If you have any questions, obviously, please let me know. I'm not going to have an assignment, obviously, today. You do have an assignment posted from last class, which is just running the random number generation and then determining if the random number generation of the flipping of a coin, heads and tails, the random number generator in App Inventor, is it a good random number generation, or is it skewed to where, maybe you have a 80% heads, 20% tails flip. Again, you want to try to get as close to 50% as possible. So I would say if you're in the range of 45 to 55, that's probably pretty good. But I'm sure you'll get closer than that. All right, so that being said, let's wrap it up. I hope everybody has a great weekend. Reach out to me if you have any questions, and we will get into our next program next week. Have an awesome weekend, everybody.